Good morning, everybody. This is going to be a great day for a Friday. I'm so excited about this video. I have got some cool things to show you. There's a lot of math, but it's algebra, so it's not too hard. So we're going to talk about the universal gravitational constant, which is also known as Newton's constant or Big G. I think we've heard Big G a lot. That's as opposed to little g, which has to do with acceleration due to gravity. You can see this formula down here that we're using. The force of gravitation is Big G times mass of the first object times the mass of the second object divided by d squared, which is the distance between those two objects. Of course, before we get too far, let's do our joke of the week. Why did Isaac Newton's son know so much about gravity? Why did Isaac Newton's son know so much about gravity? A little history. So there was an observation, which of course is part of the scientific method. If you need to know that, you can look at my video on the scientific method. So the original observation was that gravitational force was larger between two objects when the mass of the objects were greater. So you think about two objects, the larger the object, the more gravitational force there is. So this is best described as this quote, gravitational force is directly proportional to the product of the two masses. So F sub big G is proportional, that's what that little symbol is, to mass 1 times the mass 2. Again, gravity is larger between me and the Earth than it is between me and you. So then the next observation they had is that the inverse square law holds here. So the gravitational force gets smaller as the distance increases. So the further you are apart, the smaller the gravitational force is. This should be a pretty obvious observation. For example, the sun's gravity gets weaker for each planet as you get farther away from the sun. So that equation there is force is proportional to 1 over the distance squared. Okay, so if we combine those two observations, we get the force is proportional to m1 times m2 divided by r squared. So when you do proportionality kinds of things, you need to put a constant in there. So we just call it Big G. It's a constant, and it's because if you remember all the way back to your first algebra class, the equation of a straight line, y equals mx plus b. So you have the constant, which is the slope, and that constant is what we're talking about, Big G. The b part is 0, because obviously if either mass is 0, then that equation is 0. And so that's what you want as your observation. Big G, the gravitational constant, was first determined by Lord Henry Cavendish in 1798 using a torsion balance. And I think you've seen this around. Over here is a diagram showing kind of how it works. This is an incredibly difficult experiment because everything has to be balanced and level, and there's quite a bit of work that goes into it. But you might want to check out BM Furball, his channel, for a detailed explanation and a demonstration. He had several videos that go into detail about how he built a Cavendish experiment, and it's really fascinating. I'll leave a link for you. So once this torsional force balanced the gravitational force, the rod and spheres came to rest, and Cavendish was able to determine the gravitational force of attraction between those two masses, the blue balls. So by measuring M1, M2, D, and the gravitational force, then he could balance, or he could solve his equation. It resulted in an experimentally determined value for Cavendish of 6.75 times 10 to the minus 11. I know that's a tiny number, but that's part of the equation. Today, in 2020, the currently accepted value is 6.67 times 10 to the minus 11. So he was pretty darn close. This number has been verified by planetary and lunar measurements. They've worked on that, shown how it works. So any gravitational measurement in the solar system is difficult because anything with mass affects and is affected by anything else with mass. So you measure the force between the Earth and the Sun, but you have to remember there's a force between the Earth and Jupiter. So all of those things have to balance, and it's quite a tedious calculation. You can just imagine trying to do that back before there were computers. Here are some calculations that I did personally with my own observations. I wanted to see if I could calculate Big G. So my hypothesis was to calculate Big G and see how close I could be to the accepted value. So we take our equation for F of gravity from slide 1, and you remember that equation. Here it is right here. Big G times M1 times M2 divided by R squared. Then we use simple algebra to rearrange these terms so that we can solve for Big G, knowing the force of gravity times R squared divided by the mass of the first times the mass of the second. So I picked some person who shall not be named, David, and used that as my M1. So it's 200 pounds, which is equal to 90.7185 kilograms. I like that kilograms number, nice and small. So that's kilograms, and we want to convert that to newtons. Newtons is the SI measurement for force. When I convert it to newtons, I get 889.6443 newtons. And that is equal to the force of gravity. So we all know that weight, pounds, is a force of gravity. Big R, the distance between the two objects. Since this person is standing on the surface of the earth, R would just be simply the radius of the earth, which is 6.371 times 10 to the 6th meters. And you can look that up anywhere. Mass 1 is 90.7185 kilograms. Mass 2 is 5.9736. So there we have our values that we need for our equation. And there's the equation with the values substituted in. I used an internet calculator, which gave me some really good, it was easy to put the numbers in. So here's what I got. Ta-da! 6.66345 times 10 to the minus 11. Now, how does that compare to the accepted value? There it is. The accepted value is 6.67 times 10 to the minus 11. In case you are wondering, that is a difference of about 0.1%. Pretty good for a down-to-earth calculation here. So let's think about what about the force of gravity between the Earth and the Moon, and between the Earth, Moon, and the Sun. So what do you think? Will it be easy? So we take our equation, force of gravity is equal to big G times M1 times M2 divided by R squared. Here's our values for the Earth to the Moon. Of course, big G is 6.67 times 10 to the minus 11. The mass of the Earth is 5.9736 times 10 to the 24th kilograms. The mass of the Moon, 7.348 times 10 to the 22nd kilograms. I had a hard time finding that one, but that's the mass. R, the distance between the Earth and the Moon. This was also a difficult one to find. The Moon has a elliptical orbit, not a circle, so you use an average value, and that number can change, not drastically, but a little bit everywhere you look. But this is one of the numbers I could get. So again, I plug those numbers into the equation. There you see big G, mass 1, mass 2, and divided by the radius between the Earth and the Moon. And I get 1.971 times 10 to the 26. So that's the force of gravity between the Earth and the Moon. So now let's look at the force of gravity between the Moon and the Sun. Uh, so we have our equation, our values, big G, the same as we used before. Mass of the moon, 7.348 times 10 to the 22nd kilograms. That's what we used before. The mass of the sun, which is simply enormous, 1.989 times 10 to the 30th kilograms. And the distance between the moon and the sun, 1.5 times 10 to the 8th kilometers. Sorry about that. So you plug all those numbers in, and I used my calculator. By the way, these calculations and answers are cut and paste directly from the calculator, so I didn't doctor anything. So you have big G, mass of the sun, mass of the moon, the distance between them squared, and I get 4.335 times 10 to the 26. So there you can see a comparison between the gravity between the Earth and the Moon, and between the Moon and the Sun. There you have it. I was really excited about that one. Here's some more math. We've talked about big G a lot. So let's talk just a little bit about little g. So for the Earth, little g is big G times the mass of the Earth divided by the radius of the Earth squared. So this is the equation for little g. So again, we have our big G value, the radius of the Earth that we used before, and the mass of the Earth that we used before. We enter those in the calculator and we get 9.816. What a coincidence, 9.816. You can go and check if you don't know that number already. Pretty cool, huh? So, since we're all excited and we've done this once, let's do it again. So, little g on the moon, we have our equation there. Big G again, the radius of the moon, 1.7375 times 10 to the 6th meters. The mass of the moon, 7.348 times 10 to the 22nd kilograms. And so I enter those into my calculator and I get 1.623. Those are, to me, very interesting numbers. So just for curiosity, I took the acceleration on Earth, 9.816, divided it by the acceleration on the moon, 1.623, and lo and behold, I get 6, which means that the Earth has 6 times the acceleration of the moon. So just like everybody talks about, NASA, everybody that talks about that on the moon, 1/6 of the Earth's acceleration. How about that for a calculation? So what did we learn today? We calculated big G from the weight of a person standing on the Earth's surface to within 0.16%. We calculated the force of gravity for Earth to the moon and for the sun to the moon. Last, we calculated little g for both the Earth and the Moon, and we see that indeed the Moon's acceleration due to gravity is 1/6 of the Earth's. All of these values, the intermediate values that I wrote down, those can all be looked up on Google. You can check my work and make sure it's correct. And that's what we learned today. I would just give you a little side note here. Everybody wonders sometimes why the sun doesn't steal the moon away from the Earth. And you notice that our calculation for gravity of the sun, moon, and the gravity between the Earth, moon, and the sun was twice as big as the Earth, which is not a whole lot. And the fact is that the moon's velocity around the Earth is not big enough to escape the Earth's escape velocity. So that's why the sun doesn't steal the moon away from the Earth. So here's our joke of the week. I'm sure you're interested to know, why did Isaac Newton's son know so much about gravity? The apples didn't fall far from the tree. So that's my joke of the week for this week. I hope you found this as interesting as I did. We sure found out a lot of stuff, where values came from, and I look forward to seeing you on Tuesday, and we'll talk to you later.